we move on to our final gas law, which is Amontons Law. And so what that is the relationship between temperature and pressure of a gas. Here, you're going to be looking at that relationship holding the moles and the volume of the gas constant. So let's look at this relationship. So it might seem, I guess, kind of obvious in that if you had a gas, and let's say this time, because we're holding volume constant, it's in an inflexible container. So if you heat up the gas in the inflexible container, what is going to happen? Well, what must happen is that if you heat up the gas, the molecules are going faster and faster and faster. They're striking the surface of the inflexible container harder and harder and harder, so the pressure should go up, up, up. So what that tells you is that as you increase the temperature of a gas, the pressure of the gas should increase. And that means that qualitatively, the temperature and the pressure of the gas are directly related. If one goes up, the other goes up. If one goes down, the other goes down. Now, what is the quantitative relationship between temperature and pressure of a gas? Well, if you are sure to take any Celsius temperature and convert it to Kelvin, what you will find is if you double the temperature of the gas, you'll double the pressure. If you triple the temperature of the gas, you'll triple the pressure. If you have 10 times more temperature of a gas, you'll get 10 times the pressure. And so they are quantitatively related that way. They are proportionally related. And so there are some equations there that could be helpful for that. And so here I'm just kind of noting here on the basic qualitative relationship again that as temperature of a gas increases, the pressure increases. And this is Amontons Law. So what is going sort of on the molecular level? I kind of went over that, but again, if you have gas trapped in an inflexible container, if you heat up that gas, it's going to make the molecules go faster. And therefore, they're going to strike the surface of the container harder, and therefore, the container is going to feel more pressure. So it's that simple. Okay, so when you use an equation for Amontons Law, it'll be in the context where you're given a problem where you're given initial conditions of temperature and pressure, and you'll have to find final conditions, say, of a pressure for a given temperature, holding the volume and the moles of the gas constant. So there, you just a reminder to make sure any Celsius temperatures are converted to Kelvin. So here we have an example problem. So let's go ahead and do this. Okay, a gas in an inflexible can is initially at 24 degrees Celsius and 360 kilopascals. And the can has a volume of 350 milliliters. If the can is left in a car and that car reaches 50 degrees Celsius on a hot day, what is the new pressure in the can? Okay, so we have to be careful here. We're sort of given some pressure information and some temperature information and some volume information. So what we really need to do is sort of discern which law to use. And what can be helpful is just looking at what is changing and what is constant. So one thing it says in the problem that you have an inflexible can at 350 milliliters. That means in the final conditions, that can is still at that volume of 350 milliliters. Therefore, the volume is constant in this problem. Therefore, you will not use an equation that includes volume. It looks like the temperature is changing, and it looks like that the pressure, as judged by the way the problem is worded, is changing as well. So you want a relationship between pressure and temperature while moles and volume are held constant. And so that would be Amontons Law, so I'll write that here. Amontons Law, which is P1 over T1 is equal to P2 over T2. So let's go ahead and assign variables. And so we have T1, which is 24 degrees Celsius. We have P1, which is 360 kilopascals, which is a unit of pressure. We have T2, which is 50 degrees Celsius, and we're trying to find P2. Okay, so before you plug in numbers into the problem, let's go ahead and take any Celsius temperatures and convert them to Kelvin. So we have to add 273.15. And so you should at this point round to correct number of significant figures. And so what this is going to be is 297 degrees Kelvin. With 50 degrees Celsius, you're adding 273.15, and so this is going to be 323 degrees Kelvin. So once these temperatures are now in Kelvin, you can have the units of pressure as kilopascals. That's fine. Let's go ahead and now plug this in. And so we're going to solve for P2. So what we're going to do is solve for P2. And so if we're going to, we have to take T2 here in the numerator. Excuse me, it's in the denominator. We're going to have to move it into the numerator. So here we're going to have to do P2 is equal to P1 times T2 over T1. And so let's plug in some numbers. And so P1 is 360 kilopascals. And then T2 is 323 degrees Kelvin. And then T1 is 297 degrees Kelvin. And so what you see, the degrees Kelvin cancels out. We should be left with an answer in kilopascals. And I think if you went ahead and did the arithmetic, your answer would be 392 kilopascals. Thank you for listening. We will see you next time.